the building block of calculus is the concept of a limit. You will see that every result that we are going to develop in this class will somehow be related to limits. We are starting chapter 2 with limits. We are going to encounter limits pretty much in every single chapter all the way to chapter 11. So this gives you a sense of how crucial limits are to calculus. Without limits, we don't have calculus. So what I want to do in this very short intro is to give you an intuitive sense of what a limit is all about. Then we're going to go ahead and begin the actual video that will cover considerably the topic or the discussion of limits that is presented in section 2.2. Imagine that we consider the function f of x equals to x minus 1 divided by x minus 1. You're probably thinking, all right, this is silly to give a function like this. This is just simply equal to 1. The only thing that I want to caution you about that is that indeed I could cancel x minus 1 because x minus 1 appears in the numerator and denominator. And yeah, I could say that this is equal to 1. I just want us to be careful though, that this is equal to 1 as long as x doesn't equal to 1. Because if x is equal to 1, imagine, if I consider f of 1, I will end up getting 1 minus 1 over 1 minus 1, which is equal to 0 over 0. And 0 over 0 is always undefined in mathematics. In fact, in calculus, we're going to call 0 over 0 an indeterminate form. That means we cannot have an answer. An answer is completely impossible to determine. And that's because 0 over 0 is undefined. So as long as we understand that this function is equal to 1 when x doesn't equal to 1, then you can go ahead and cancel x minus 1. So graphically, what does that look like? All right, so let's go ahead and do that. Graphically, here we're going to have the x-axis, the y-axis. Let me label that. So this will be y, this is going to be x. And we know that f of x right here is equal to 1 for every x as long as x doesn't equal to 1. So if I want to sketch this graph, then I will make sure that when x is equal to 1, let's say that y is right here as 1 as well. When x is equal to 1, I am going to place an open circle. And an open circle really showing that my graph, my function, is undefined at 1. But then I know that for any other x value, to the right of 1 or to the left of 1, the y value is going to always remain at 1. So I'm going to go ahead and sketch my graph as a horizontal line passing through 1, and then same thing on the right like this. So I know that this will be the graph of my function. In fact, this is going to be the graph of f of x equals x minus 1 divided by x minus 1. So there is my graph. And as I said, other than this, there's nothing else that is interesting. The graph is showing that the function is undefined at 1. There is an open circle. And then it shows that for any other x value, whether the x value is to the right of 1 or to the left of 1, the y value is going to be 1, no matter what. So now then, let me ask a more interesting question. And this is exactly where the concept of a limit will begin. We already know that the function is undefined at 1. So what happens at 1 is completely uninteresting to us. A more exciting question is, what happens around 1? Very close to 1. as x approaches 1 from the left and as x approaches 1 from the right, what is happening to the y values of the function? And honestly, this is the concept of a limit. Imagine that we are somewhere here on the left of 1. Let's say this is our first x value, and this looks like 0.6. We ask the question, what is the y value when x is equal to 0.6? And this is so easy to determine. You just go up to your graph, and then you know that the y value is going to be 1. But you want to figure out, though, you want to keep moving closer to 1. The closer you can possibly get to 1. So then now pick an x value that is closer to 1, something like this one over here. Let's call it x sub 2. And x sub 2 could now be something like 0.7. So therefore now, what happens to the y value that corresponds to 0.7? You go back to your graph all the way up, and then you notice that it's going to be 1 again. And you keep moving closer and closer and closer to 1. And as you move closer to 1, as x is approaching 1 from the left, right here from the left, you notice that the y values are getting closer and closer to 1 as well. The same thing is going to happen as x approaches 1 from the right. So now, imagine that we're somewhere here. This is your x value. Let's call this x sub 3. This x value could be something like 1.4. You're going to ask the same question. When x is equal to 1.4, what is the y value? So you go up to your graph and you notice that the y value is 1. But remember, you want to keep moving closer and closer to 1. So now you're going to consider x values that are here, and then closer and closer and closer. And seriously, you want to be able to get very close to 1. So eventually you're going to go 1.1, 1.001, 1.0001, 1.00001. Hopefully you get the point. X is getting really, really close to 1 from the right. You notice that the y values are exactly 1. So then what you notice is that no matter how you approach 1, whether you approach it from the left or from the right, the y values from the left over here and from the right are exactly 1. So that's very important. Again, x is approaching 1 from the left, x is approaching 1 from the right. Look at the y values. The y values consistently are equal to 1. And because of this, we say that the limit of the function as x approaches 1 is equal to 1. Symbolically, this is how we write it. Limit, the word limit, will be abbreviated with LIM. So we will say that the limit as x approaches 1 of the function, in this case x minus 1 over x minus 1, is equal to 1. Sometimes we put brackets around the function just to keep it nice and more contained, but you don't have to put brackets. Sometimes we get a little bit lazy, and instead of writing the actual expression of the function, we just write f of x, and this is also a fair game. You can do that. So again, this is saying that the limit as x approaches 1 from the right and from the left of 1 of the function f of x is equal to 1. And this notation is saying the same thing that we just spent quite a bit going over. This notation says, let me put an arrow over here. This notation is telling us that as x approaches 1 from the left and from the right, the values of the function are approaching 1. In this particular case, because the function is constant, the values of the function, the y values, are exactly equal to 1. So this output that we talk about, this one refers to the y values. Okay. As x approaches 1, the y values are approaching 1. But because the function is constant here, the y values are equal to 1. Here is another great example about how we interpret the limit of a function as x approaches a particular value. For example, look at this function right here, g of x. According to the way in which this function has been defined, g of x is the quadratic x squared, the simple parabola x squared, whenever x does not equal to 2. But if x happens to equal to 2, g of x is going to be equal to 1. Graphically, how will that look? What I'm going to do right now is I'm going to sketch x squared, just simply x squared. We learned how to sketch x squared a long time ago. So I'm going to start with 0. When x is 0, 0 squared is 0. When x is 1, x squared is 1. When x is negative 1, 1 again. When x is 2, I am not going to put a dot. I'm going to put an open circle because remember how the function has been defined, that if x is 2, the value of the function is not going to be 2 squared, it is going to be 1. So here at 2, I am going to put an open circle indicating that the y value of this function is not going to be on the parabola. When x is negative 2, then the y value is going to be 4. So that point is going to be there. So the graph is going to be in a U shape, like that. And then in the other direction, again following the typical U shape of a quadratic function. Then when x is equal to 2, right here, we know that the y value is going to be 1. That means that there is going to be a closed dot, a dot that is just floating within that xy plane. Nonetheless, this is the entire graph of g of x. The graph of g of x consists of this parabola with an open circle at x equals 2. And then at x equals 2, we have to have a dot right here indicating that when x is equal to 2, the value of the function is exactly 1. The y value is 1. So then, obviously, something very interesting is happening at 2. I will even circle that. I will just circle x equals 2 there, because this is showing that when x is equal to 2, the y value is not as predictable as we would hope. The y value is not equal to 4. The y value is equal to 1. From the point of view of a limit, though, we don't care what happens at 2. We only care about what happens around 2. So for example, when x is approaching 2 from the left, I notice that the y values, let's look at the y values. I notice that the y values, let's say, of the function lie on the parabola. Then, when x gets even closer to 2, the y values are climbing a little bit higher up. And then the closer I go to 2, the higher the y values are getting on the parabola. And those y values, notice that those y values are approaching the circle, the open circle that is on that parabola. And that open circle happens to be at the same level as y equals 4. Similarly, in the other direction, as x approaches 2 from the right, when I take this x value right here and I go up to my graph, that takes me somewhere there. Then, as x is getting closer and closer, the y value is a little bit now lower. Then x over here gets closer to 2. The y value is getting closer to the open circle. Then I continue like this, and you can really see now, hopefully you can see that the y values are also getting closer and closer to the level of 4 right here. Even though, let me remind you, even though the y value at 2 is exactly at 1, when x is approaching 2, the y values are approaching 4. They're not approaching 1. The y values are traveling along the parabola. So along the parabola, the y values are right here approaching 4. They will never equal to 4. But from the point of view of a limit, we don't really care what happens at 2. We care about what happens around 2, in a small neighborhood around 2. And in a small neighborhood around 2, let's say right here, the y values are getting closer and closer to 4. I wanted to show you here with my graphing calculator. I went ahead and I plotted the function, and I looked at the table feature. I wanted to see what happens around 2. And notice how around 2, when x is equal to 1.9, so we are on the left of 2. The y value is 3.61. And then as x gets closer and closer to 2, 1.9, 1.99, 1.999, look at the y values. They're approaching 4. Then I went and I took x values to the right of 2. So again, we're getting closer and closer to 2, but from the right. 2.1, 2.01, a little bit closer to 2, 2.001, even closer. And I want you to look at the y values. Look at them. From 4.41, then to 4.04, 4.004. So clearly, again, the y values are approaching 4. At 2, when x is equal to 2, the y value is not equal to 4. But we don't care about what happens at 2. We only care about what happens around 2. And as we get really, really close to 2, the y values are getting closer and closer to 4. And that's what we want when we talk about limits. That's what makes 4 the limit of this function as x approaches 2. The fact that as x approaches 2, the y values are consistently approaching 4. So symbolically, we're going to say that the limit as x approaches 2 of the function, actually it's not f of x, it's g of x, that limit is going to be equal to 4, not to 1. Because the y values, again, I know that I'm repeating myself, but I really want to make this clear. As x is approaching 2, so x is not equal to 2, but x is really getting close to 2. The y values are the y values on the parabola. And those y values are getting closer and closer to 4. Notice how we are approaching the open circle, and the open circle is at 4. And that's what the limit is concerned about. The limit a function has a limit if the y values are approaching the same number. So x is getting very close to 2. The y values are getting very close to 4. So then we say that the limit as x approaches 2 of the function g of x is equal to 4. And this is very striking because this is really showing that the limit of a function as x approaches a number doesn't have to be equal to the y value. So my function can be perfectly defined at x equals 2. Like in this case, at x equals 2, the y value is 1. But the limit of the function at 2 is not equal to 1. It's actually equal to 4. So this is something that is unexpected as we're learning about limits. And something that I really want you to see and to feel comfortable with, that even though we know that g of 2 is equal to 1, the y value is equal to 1 when x is equal to 2, great, that's great. But that doesn't mean that the limit at 2 has to be 1. The limit is all about what the y values around x equals 2 are approaching. And the y values are approaching 4. They are not approaching 1. So this is why the limit as x approaches 2 of g of x is not equal to the y value. As we said above, the limit as x approaches 2 of g of x happens to be equal to 4, not to 1.